my very great pleasure to introduce our next speaker. There have been some great presentations today. I'm sure this is going to be another one of them. Dr. Fernando Rios-Avila is going to be talking about difference in differences and his views on and some new developments in that area. So looking forward to this. Thank you very much.
Thank you very much. First, just want to make sure that everybody can hear me.
Yep.
Excellent. So first of all, thank you very much for the invitation. As it was said, today I'm going to be presenting a little bit of a background and some of the steps, the way I like to think about it, on how this particular command, JWDID, can help you tackle some of the problems that we ask or what that you may face when you do difference in differences with the staggered designs. So let me start. So why difference in differences? As many of you probably already know, difference in difference is one of the most popular designs in applied macroeconomics because it requires relatively few assumptions to identify the treatment effects. You have the no anticipation, the parallel trends, and no spillovers. And those assumptions, you should be able to estimate something that resembles or that is close to that treatment effect, to the impact of a policy that you're trying to analyze. So this approach is so simple that I remember back when I was actually learning about this for the first time, I wouldn't really even put too much emphasis on the methodology because it was something that you could do with a simple regression, dummy for treated, dummy for the before and after, an interaction of that, and basically you're done. What is interesting about difference in differences, especially when you think about doing this with linear models, is because OLS it's able to tackle any kind of data, you can use the methodology to analyze the treatment effects of almost any kind of dependent variable, even if they are limited dependent variables. So you could technically do it for binary variables, count data, etc., under certain assumption, of course. Now, the canonical DID design, just to remember how it works, it follows more or less like this. We're going to assume that there are two groups, one that is the treated and the other one that is the control. And we're going to assume that these two groups are going to be observed over two periods, pre-treatment or T0 and a post-treatment T equal to 1. If we assume that there is full heterogeneity, we can say that the outcome, the potential outcome, is going to be defined by this regression over here, which basically says that your outcome today is going to depend on some fact that is yours, some growth that you can experience across time, and some effect that could be dependent on how you react to the treatment. Of course, these are the potential outcomes, meaning this may happen regardless or not of if you are treated or which point in time we are looking at you. We just need to know if you are part of the treated group or the control group, so we can tell you what your potential outcome is going to be. Reality is not that simple, however. We only see one of the outcomes. That means if you are treated, we're going to observe your outcome as treated. If you're not treated, we're going to observe your outcome as non-treated. So in this framework, if you want to think about how to estimate the treatment effects, it's very straightforward. You will be able to see all these potential outcomes. The only thing that you need to do is look at the outcome under treatment status, subtract the one without treatment, and that's the treatment effect for that individual that can be measured only in the post-treatment period. Of course, this is very too much detail, and it's going to be very difficult to identify. So most of the time, we try to summarize this into a single number, which is the average treatment effect of the treated. You could also estimate this for the average treatment effect or the treatment effect on the untreated, which is nothing else than taking the expected value of this parameter over the group of your interest. Again, most of the time, the treated group. The problem with this is we still have a situation where the treatment effect, even the average treatment effect, is not identified because we cannot observe what is the outcome under non-treatment for the groups that were actually treated. So how do we estimate this component? The way I decided to, when I was working with this and understanding how it works, is that it's useful to make a decomposition on what is the post-treatment without treatment status. So this is going to be decomposed into two components. First, it's what was the outcome without treatment in the pre-period. And second, what was the expected growth that this group would be expected. Now, we still have a problem that we do not know what these parameters are. So we need to impose those assumptions to identify it. The first one is the no anticipation, that basically says the expected value under non-treatment for the treated group is going to be exactly the same to the expected value under treatment before treatment happened. So they are not anticipating the effect. Therefore, their outcomes should have been the same regardless if they were put in the treated group or the non-treated group or the control group. So we're just going to say we can just take the expected value before treatment for the group that end up being treated, and we can substitute that here. The second one is the parallel trust assumptions that says we're going to assume that in average, the growth that is experienced by the group that became treated under, or if they were never treated, they should have experienced the same kind of growth than the control group experienced. Okay, so we can substitute this that we didn't know with this component that we can observe because we have a control group, and we can substitute it by here. So putting everything together, you get that expression that most of you probably already know quite well on how to estimate the AT&T with differences, which is nothing else than comparing the the post minus pre outcome for the treated group, and to that subtract the same component from the control group. How is this estimated? So we're going to put aside the problem of standard errors, because standard errors on their own are a different beast altogether, and most of the time we're just going to rely on software. But if you would be only interested on the AT&T, or sorry, on the ATT, at the end of the day, you just need to make this kind of comparisons of means, and you will be done. But if you want to make a regression, and this is the regression that I was saying before when I saw it the first time, it seemed too simple to pay too much attention, is that you can estimate the same average treatment effect by just using a dummy that says if they are part of the control or the treated group, a dummy to indicate if they are in the pre or post period, and an interaction of those two, where this theta will represent the average treatment effect. Of course, life is complicated. This canonical example where you have two periods, two groups, doesn't always happen. We have a situation that is much more complicated. For example, we may have situations where you have not only a few groups, but a number of groups, individuals or groups that could be followed across time. You may also have access to multiple periods. You may want to control for characteristics because you're interested on other covariates that could be explaining the outcome, and you want to make sure that your groups are similar once you control for them. Treatment could be staggered, so it's not that everybody's treated at the same time. People might be experiencing the same treatment at different points in time, and that will have an impact on how you should estimate the treatment effects. And of course, what if the treatment, if the outcome that you're interested in is not a limited dependent variable? So life is complicated. There has been a lot of discussion about all the problems or all these questions and how to solve them. But even with all those complications, we like to make our lives even harder. So what if we are interested on heterogeneity of the ATTs? With this, I mean, what if I want to see if the effect of the treatment is stronger for some groups? For example, if I'm analyzing a training program, I want to see if the impact is stronger for men compared to women, or for white versus non-white individuals, for people with higher education versus lower education, etc. You may also be interested on thinking about those treatments. What if the treatment is not the same amount for everyone? So some people might receive a full treatment, Some others may receive only 50% of the treatment, only 25% of the treatment. And we would like to analyze and take that into account when estimating the treatment effects. And something else that usually comes up a question is, what if people are receiving full treatment, but they are just receiving different kinds of treatment? So one group may be receiving a transfer in terms of a cash transfer, another may be receiving the same kind of treatment, but or in terms of an in-kind transfer. Which one has the stronger impact? No. Thanks to the research of Professor Wooldridge and some of the advances and developments that has happened over the last few years, and some of my own based on the understanding on how the methodology works, is that the JWDID, or also known as the extended two-way fixed effects, can help you answer a lot of these questions. So just to make a setup of all of these, and I'm going to try to keep the setup consistent for the rest of the different scenarios. Let's assume that we have the situation for that we have access to panel data. In other words, individuals are followed across time, and you know which individual is going to be followed across time. So this is in answer to the first question. What did you have individuals that you can follow across time? So the easier option is going to be that instead of controlling for your treatment, non-treatment status, you can control for individual fixed effects. So you can control for this, and you can forego now the treatment variable. So this is something that, again, comes as a question all the time. Why, when you introduce individual fixed effects, your treatment variables appears? It's just part of the specification. You're moving from one event to one status to the other. Instead of controlling groups for treatment, you're just controlling for individual fixed effects. Interestingly enough, however, if you have a balanced panel, each observation is observed across for the before and after, the results that you're going to obtain from one methodology to the other are going to be exactly the same, with the small differences perhaps in terms of the standard errors and depending on how you estimate. What about if you can follow individuals across time? Under the assumption that everybody is treated at the same time, well, the treated group, everybody in that group is treated at the same time, you can extend this easily by, instead of estimating a treatment, a coefficient for the time variable, you just say, I'm going to introduce time fixed effects, and you're done. Perhaps the only difference that I would like to emphasize here is that you no longer will have an interaction between the pre and post. It's going to be easier to call this just a dummy variable that takes the value of 1 once a unit is in the post-treatment period and 0 otherwise. So this estimation is still possible to do it with a simple OLS. And also, this particular specification is what is known as the infamous two-way fixed effect, or the generalized two-way fixed effect, that difference in difference approach, which, again, it works as long as the treatment happens at one single point in time. What do you want to control for characteristics? Now, the canonical assumption assumes that the parallel treatment effects or the parallel trend assumption holds. And the implicit assumption of that is that either the treatment effect is homogeneous across the characteristics, or that the treated and the control groups are going to be similar in characteristics. But what if that is not the case? Well, what you can do in order to avoid that problem is simply to control for those characteristics into your model specification. And what most people do is to just add linearly the characteristics in your model. This is a very simple extension, and unfortunately, it imposes some assumptions that we may not always be aware of, which is that the treatment effect is going to be assumed to be constant regardless of the characteristics of the individuals. And again, if the assumption is correct, you have no problems. But if the assumption is incorrect, the weights that you're going to be applying to estimate this treatment effect might bias some of your results. So what is the alternative approach? Well, there are a few solutions. One option is just to, again, by assumption, is to assume the treatment effect is constant across characteristics. Therefore, just use the specification that I have here, and you're done. But the other one is to move from the parallel trends assumption to the conditional parallel trends assumption. The difference between one and the other is that the parallel trends assumptions just says that the growth between the treated and the control group are the same in absence of treatment, whereas the conditional parallel trends assumption says we're going to look at the same growth, but conditioning on characteristics. So we want to compare men with men, children with children, high education, people with higher level of education with people with high level of education, etc. What does this imply for us? That you can technically estimate this average treatment effect for as a function of the characteristics themselves. Of course, this still will be a lot of heterogeneity. So most of the estimations, including JWDID and CSDID, will typically provide you just a single number that is nothing else than the expected value of the average treatment effects that you would estimate for each characteristic. Now, how exactly you do this empirically? First, I'm going to talk about how would you do it for the empirical case, which is the 2x2 case. And there are at least two solutions, or a few solutions, some of these proposed by Santana and Xiao in 2020, which are do an outcome regression approach. So separate all your treatment, control, pre and post periods, make your models on each one of them, and then use the predictions of those models to do your difference in differences. The second one is using inverse probability weighting, where you balance the covariates, and then you are able to do the simple diff in diff approach, or do a combination of both, doing what is known as the doubly robust. You do a regression, but you also control for difference in characteristics using the inverse probability weight. Now, Wooldridge, on the paper that introduces the extended two-way fixed effect, he implicitly also suggests the following. If you would like to do the same thing as Santana and Xiao said, specifically the outcome regression approach, the only thing that you need to do with your specification is make it more flexible. So this is what we normally have for a standard difference in difference approach. But if we want to control for characteristics, we just need to include the characteristics in levels, interacted with the treatment dummy, interacted with the time dummy, the pre and post, and interacted with the interaction of the pre and post dummy. And that's it. Perhaps the only difference, and I left that here with blue, is that this particular parameter, you can either use the d-mean version of it, but this is not necessary. We are going to demean it only if we want to have a clean interpretation of theta. If we do not demean it, we can still estimate theta. We just need to go to additional steps. Now, a question that comes any now and then is, what should we include as this type of controls? Well, this is a tough question. The typical answer are that first, as you can see here, we have to add a lot of interactions in order to have a flexible model that accounts for the conditional parallel trends assumption. That means that the more variables you include, the more interactions you will need to estimate, and that would leave you with very few degrees of freedom to actually estimate the precision of the parameters. So unless you have large panels or repeated cross-section, probably you want to think about only fewer controls. Now, if you have panel data, you should aim for controlling for pretreatment characteristics that are time fixed. These to avoid the bad controls or controls that could be affected by the treatment and could create a bias in your estimation. However, you could also use time-varying variables, but you have to do it with caution. Well, the reason why you can use it is in the scenarios like repeated cross-section, variables or time-varying variables, anything that you're going to control is going to change across time, so you cannot really avoid it. But you need to at least think about that if there is any variation of those time-varying variables, that variation should remain stationary, or that whatever change you're observing, you have to make sure that those changes are exogenous to the treatment. Now, from the programmatical point of view, you're doing this using CSDID, and you're using panel data. The command is going to force you to estimate time-fixed characteristics, but it's not going to do so if you use a repeated cross-section. However, if you decide to use JWDID, it's not going to import this restriction, so it's always going to treat your data as if it is time-varying. You're the one who has to pre-prepare it if you want to assume that it's going to be time-fixed. Okay, so here's where we come with the fall of DID. So what happens if the treatment is not applied at the same time for all the units? This is what is typically known as the staggered treatment effect. So one group is going to be treated earlier. The second one is going to be treated a few periods later. A third one is going to be treated even later yet, etc. A note here, perhaps, even if you were treated earlier or later, once you are part of the treated club, you always remain treated. So you cannot have reversals. Now, the traditional approach to do this, or to apply, to analyze this staggered treatment effect or staggered design, was to use the quote-unquote generalized dual fixed effects. That was nothing else than adding the individual treatment effects, time fixed effects, the indicator, as I was showing before. However, this approach only works if the treatment effect is constant over time for all units. But because that's not guaranteed, it's very likely that if you're using this approach, your results are going to be biased. Why are they going to be biased? Well, one way of thinking about it, if you're going to estimate the treatment effect using the regression approach and using ordinary least squares, the way that OLS is going to identify theta is by comparing pre and post outcomes using various 2x2 designs that are there in your data. That means that you're going to be contrasting units that change their treatment status from not treated to treated. That's a good change. And for now, we're going to ignore the fact that there could be some reversals. But it's going to do this contrasting for identification of theta by looking at the groups that were treated or that have experienced this treatment status change to those who are not experiencing any change on their treatment status. That means that those groups are the never treated. This is going to be a good control group. The not yet treated, still a good control group. And the already treated, because they are not changing the status, but they have already been affected by the treatment, and therefore very likely that the PTA is failing. And this is what causes having a bad control group. Now, this has been interpreted in two ways, that we're using a bad or incorrect control group because they are already treated, or because we're using an already treated as a control, we technically have to apply them, or we have to give them a negative weight to be able to put them as part of the control group. What solutions are there for doing this? And I apologize, I just realized that some of my references are not appearing on the slides. So I will be updating that before sharing the slides. Well, what solutions are for the problem? I have classified them in at least 3 approaches. One of the approaches is, if you want to avoid the bad controls, just use pretreatment data or data that is not affected by the treatment to create these counterfactuals. Use that to make predictions, and then use those predictions to estimate your treatment effects. That's basically what DID2S and DID imputation do. The other approach is to use controls to make sure that you're only using good controls when estimating the average treatment effects. So always excluding the whatever resemblance of a bad control is. And that is what Callaghan Santana provides or suggests, and that is implemented using CSDA. The third approach is to try to achieve 1 and 2 by making a better and moderate specification of your model. And that is basically what Wooldridge provided, or what Wooldridge suggested on these three papers that unfortunately are not coming up right now, and that we once again reiterate with the paper with JWDID 2024. Okay, so this is how the idea behind JWDID comes into being. So what Wooldridge tells us is that two-way fixed effects was not really wrong. It was just too simple. We're trying to do this model that was assuming that everything should be summarized into a single indicator. However, because we are already assuming that the treatment is coming at different points in time, and that is affecting different groups at different points in time, a better way to account for this would be to have lots of interactions that would depend on when a group is treated and which group is treated. So once again, the problem with the two-way fixed effects was not so much the two-way fixed effects, but that we were oversimplifying how should we accounting for the treatment. Now, this basically tells us that this theta GT is going to be capturing the ATAT. That is going to be by specification. It can vary by group and time. And for this specific or this particular specification, assuming that all not yet treated units are going to become our controls. And when I say not yet treated unit, it includes the never treated units. So you're interested in a model like this, you will have to estimate the model using just JWDID, indicating what is your time variable, your panel data, and your group variable. One problem with the specification, it already assumes that the parallel trends assumption holds. So what if you want to test if the parallel trends assumptions hold or do not? Well, in that case, you can extend the specification and not only include the interactions on the post-treatment for the post-treatment periods, but also include for all the pre-treatment periods. Doing this basically says that the only group that is going to be considered as your control are going to be the never treated units. Technically, this is exactly the same thing that you would get if you estimate this using Caravan-Santana and CSDID with regression with the never as controls. And it's also what Sun and Abraham suggest, except that in that paper, they do not use absolute time to do the interactions, but relative time. Now, if this is the interaction or the specification that you're interested in, you just have to indicate never to specify that you want only the never treated to be your control groups. The next question is, what if you have repeated cross-section? How can you apply to this? How can you modify your model? Because you have repeated cross-section, you cannot estimate individual fixed effects, but instead you could estimate group fixed effects. So instead of estimating individual fixed effect, we're going to estimate for all group fixed effects. And in the specification in your model, you just have to exclude any resemblance from I bar. So whenever with the command you exclude the I bar, it means that you're deciding to do you're deciding to treat the data as it would be repeated cross-section. The problem with this specification, however, is that you're going to have a lot of estimations for the ATTGTs. So how do you aggregate all of them? Well, JWDID produces too many treatment effects. So you really want to analyze it and get more power by pulling out some of those estimations, you can just aggregate them. And the aggregation that happens on the background is nothing else than a simple weighted average of the treatment effect of interest, assuming that they are part of the group that you're interested in. For example, for a simple ATT that has the average treatment effects for the whole population or all the population of your data, you're just averaging the treatment effects, assuming that they were treated, And the weight that you're going to be applying is for each group and time, how many observations you have in that data. You can do the same by group, by summing up or by averaging out the treatment effects across all periods for a specific group. The same for the calendar. And for the event, the only difference is that you're looking at always making sure that the difference between the time of analysis and the cohort is equal to a particular value. That's it. What do you want to control for characteristics? Just like in the 2x2 scenario, you need to add a lot of interactions. And again, this is where you have to think about if it's really worth it to add more interactions to the model, because you may have to add the variables as themselves, interacted with the cohorts, not with the individuals, interacted with all the time dummies, in addition to interacted with all the time and cohort dummies. Now, some considerations when you look at this specification. First of all, you have some variables that are fixed either on time dimension or the cohort or individual dimension. They're going to be dropped. So you don't have to worry about them. The command itself, I already included some specifications, so it doesn't provide redundant variables, at least most of the time. Second, again, this XIT, you can decide to either include it or exclude it, or include it as it is or not. You include it as it is, this is no longer an ITT. If you demean it, this becomes once again your ATT-GT for the specification. Finally, this parameter, the delta GT, is going to be the impact that X has on the ATT for that particular group. How to do this in Stata? You're trying to use it with JWDID. Well, I should have included here the examples for controls. But if you want to do this, the specification that demeans the data, you use it as it is. If you prefer to use the data as it is, which might save a little bit of time and computation instead of demeaning the data the first time around, you just say X as is, and that will produce the second model. Again, the only problem with that is that the parameters that you obtain as the theta are no longer ATT-GTs. But if they are no longer ATT-GTs, how do you estimate the average treatment effects? Now, this is something else that you might find useful when thinking about how these are estimated, because the ATT-GTs, they resemble the prediction approach of Borjak, for example, because what you're trying to do is estimating the difference between the prediction under treatment and the prediction without treatment for each group. So you average these. It doesn't matter if the X's were demeaned or not. You're going to obtain the average treatment effect conditional on those X's. Limited dependent variables. So, as before, because we're using an OLS, the big advantage is that you can use any kind of outcomes with the minor inconvenience of either heteroscedasticity or nonsensical predictions. However, if you decide to do that, you need to be aware of that one is implicitly assuming that the parallel trans assumptions or the conditional parallel trans assumptions hold at levels, but that may not always be the case. One of the examples that is out there is that what if, for example, wages for two groups, the treated and the untreated, they all grow at the same rate for the treated and the control, but the group with high earnings, their wages are going to grow faster in absolute terms, which means, or with might suggest that the PTA does not hold. So the suggestion from Wooldridge in this case is that instead of focusing on the outcome itself, it's going to be better to focus on on the latent variable and to verify if that is holding. So how does it change the specification? That instead of looking at the outcome itself, we're going to still be using the same specification for the modeling, but we are going to be relating the latent variable with some nonlinear function to the expected value of the actual values of interest. One way of thinking about it, if you use Stata or you're familiar with the terminology, is to think about generalized linear models, where your G is the transformation or the link function between the latent variable and the expected value of the outcome. So this could be a logit, Poisson, Tobit, etc. So that's the first consideration that you need to make when considering estimating DADs with limited dependent variable. The second consideration is that when you have nonlinear models, it's not going to be simple to add fixed effects. It's not simple because it creates the incidental parameter problem, which means you do not have enough data to identify the fixed effects. And because you do not have data to identify them correctly, there is going to be some contamination when you're trying to estimate the parameter of it. To avoid this problem, there are two possible solutions that you can take. One is to use instead of using individual fixed effect, is to use group or cohort fixed effects. That is going to typically reduce the amount of fixed effects you need to estimate. Or the second approach is to use the correlated random effect approach or correction, which is an alternative to fixed effects. In this case, this parameter delta G is not the ATTGT on the outcome, but it's going to be the ATTGT on the latent variable of the outcome. What happens when you use JWDID? If you want to change the model, the only thing that you need to do is saying what particular model you want to use to analyze your data. I have tried to program it so it's flexible and will accept most commands, but at some point you have an issue, let me know. One of the problems that I had earlier on, for example, was to use two-word commands like fractional logit to do the estimation. And for all the estimation methods that did not accept the cluster variable to cluster standard errors, but they will require the VCE open parenthesis cluster variable to do this correct standard errors. But when you use method, the command will automatically drop your individual fixed effects and instead using cohort fixed effects. The only one that doesn't do that is if you decide to use the PPML HDFE so far, which will still add individual fixed effects even though the outcome is assumed to be a count mode. The second approach is to use, again, the CRE option, which is nothing else than saying CRE, it will automatically estimate the mean variables for each variable in the specification and correct it for you in the model. The aggregation, just like before, stat, simple group, calendar, and event. If you do not include anything, the method or the command will estimate the marginal effects or the average treatment effects depending on what are the defaults of the command you're using. For example, if you use a logit, it typically is going to use the predicted probability to estimate the effects. So if you're interested on the effect of the latent variable, you have to be explicit and say, I want to predict the latent variable. Once again, what if you're interested on X heterogeneity? In other words, you want to see what happens if one group or how the treatment affects one group con respect to the other. In your setup, you can add all the variables that you need. They will automatically be included with all the interactions in the model. But if you want to make the estimations and look at the heterogeneity, you can do it in two ways. If you're just interested on the simple estimation, you can say something like simple over x1, because it's a categorical variable, and this will estimate the ATT for all the groups defined by this variable. if you're interested on any of the other aggregations, calendar, groups, event, etc., you could use the all res option that works like an if option. You're basically saying, I want to estimate the average treatment effect, the event estimations for a group such that x2 is bigger than 0 and x bat less than 1, or where x1 is equal to 0. So you're adding an additional constraint on the data and saying, I want you to estimate the average treatment effects only for that group. Treatment intensity. So another common scenario that people ask and usually request on how can you do this with the newer commands is, what if you want to do this for a treatment that it's a dose, or you're trying to allow for different levels of intensity of a treatment. Specifically, let's say that you assume that your treatment goes from 0 to 1, and you want to consider that when analyzing the treatment effects. The other option is to say you just know that there are different treatments and you want to analyze all of them at the same time. JWDID allows you for both scenarios with some assumptions. For the case of intensity, for example, it allows you to account for treatment intensity, but it's going to impose the assumption that this ATTGT TI is going to be a function. This ATT is going to be a function of the intensity, but this function is going to be linear with respect to the treatment intensity. This could be relaxed to some extent. It's still under experimental procedures. So right now, we are assuming that it has to be linear with the treatment intensity. Now, if you want to do that, the only thing that you need to do with the specification is include another option, TRT bar, that will provide another variable that will define what's the intensity of the treatment. In order to make the aggregations, in this case, you have two options. The first one is using the standard or the default specification, and this will estimate the treatment effects, assuming that all units will have the full treatment intensity. So it's going to make the extrapolations for the ones who were just partially treated, if you mind. However, if you want to see what happens with the treatment as observed, you just need to say as is. All of these can be combined with the same options as before, of the other restrictions and the other option, or the other option. Treatment heterogeneity, which could include the on and off situations. The most flexible model in this scenario would be to just include an additional interaction to all the cohorts. And that's what it would allow you to do. You would have to estimate not only changes by group, by time, but also by the heterogeneity of the treatment that you're looking at. With JWDID, this is as simple as saying, I want to add heterogeneity to the ATT variable. In this case, for example, let's say that I have a treatment with 3 levels or 3 different treatments. I'm going to assume that the middle treatment is my baseline and only include the dummies for the other 2 groups. For aggregation, once again, you have the same specification as before, or that can be combined with over or always. Statistical inference. And good, because we're almost at the end. So for a statistical inference, the only thing that you need to be aware of is one of the suggestions from Wooldridge is that when you estimate the aggregates, probably you want to use the unconditional standard errors. That is valid and possible, but only if you do not absorb fixed effects. So if you use something like RecHDFE, which is the default, or PPMLHD, you cannot use unconditional standard errors to estimate the aggregate average treatment effects. However, you could use regress method with CRE or Poisson with CRE. This first one is what Stata currently does, for example, to estimate the Wooldridge approach and estimate with the correct BCA unconditional standard errors. I'm going to leave the other details for other options that are really more advanced. And just closing with this, as you know, there was a huge battle of methodologies with two-way fixed effects and how they should be applied. At this point, I believe they have settled down with a few of the commands out there. I'm glad to say that I have two of those, and well, that I am trying to still keep up with two of these approaches. And there's some assumptions. All of these actually will provide you the same results, and some of the methodologies are more flexible than others. My intention when starting to write the JWDID was not only to learn what was going on behind, but also to make it as flexible as possible. And to some extent, I was able to get extensions that go or that went beyond of what Professor Wooldridge proposed, or to some extent that we both developed independently, in my case, from the applied approach, whereas Professor Wooldridge has been doing this more from the theoretical approach. In any case, I hope you find it useful. I will share all of these. And if you want to estimate or you want to install the command using some of the latest features that I mentioned, you will have to download it from my repository. I just haven't had time to push it to SSC. Thank you very much.
Thank you very much, Fernando. That was a fantastic presentation, a very rich and interesting presentation with a lot to chew on, which I think is appropriate for our last formal presentation before lunch. I know that we've got a gift which we would like to give you in acknowledgement of this wonderful presentation, and I believe that'll be sent out by post. So thank you very, very much. If people have got questions, presumably they can email you and you can have a dialogue with people who might want to ask you questions. I'm really looking forward to experimenting with a few things with JWDID. Thank you very much again, Fernando.